Good morning, everybody. Welcome to the MPG Primer today. We're really excited today to have Haodong Tian. He's a postdoc researcher at MGH in the Broad Institute in the lab of Pradeep Natarajan. He's previously completed his PhD in biostatistics at the University of Cambridge under the supervision of Stephen Burgess. His research focuses on developing innovative causal inference methods, particularly for Mendelian randomization, and applying them to address real-world biomedical questions. He has broad interest in the interface of statistics, epidemiology, and genetics. And we're happy to have him here today. And again, ask questions throughout. Thank you. Take it away.
Thank you. Okay, thank you, everyone. So today, let's talk about Mendelian randomization. So our story starts with a very important question, that is the causal inference question. So we are not familiar with the general inference. That is about the association between X and the exposure X and the outcome Y. So in other words, this is the probability of the Y given the observed exposure X value. But causal inference is kind of different, or essentially we can say totally different. That is about the probability of Y after we change the exposure. So that is about the change of the exposure, not the observed exposure. In other words, when we say there exists a causal effect of exposure on the outcome, it means that if we change the exposure, the outcome will be changed accordingly. So causal inference is very important and very natural questions in many scenarios. So the essential idea is that the causal inference will give you the motivation to give interventions on the exposure in order to improve your outcome. So that's the essential ideas. But this is difficult. I remember when I first took the course of simple linear regression. At that time, I really wish that the fitted parameter of the regression have the causal interpretation. But obviously, I was wrong. The reason is that the regression or the simple linear regression essentially is about the association. But association between the X and the Y doesn't mean that there exists causal effect of X on the Y. In the sense that you change X, your outcome will not be changed. So in other words, if you use the graphical language, it means that there's no arrows from X to Y. So there are many examples that can illustrate that X, Y are associated, but doesn't mean that it's causal relationship. So the most famous example is the confounding structure. So the confounders here refers to the variable that can affect your exposure and outcome jointly, so that you can observe that X and Y are associated, but it doesn't mean that it's causal effect. So that's why we need the causal inference methods beyond the general inference methods. So there are many important causal inference methods, and I think the most reliable and convincing examples is based on the experimental data. So we're not familiar with this because RCT is very good, and we like the RCT because it does a perfect randomization. It can have the very good causal interpretation, it's very intuitive, but it is expensive and sometimes it's not plausible. That's why in the past 20 years, the main development of causal inference methods is based on the observational data only. We have lots of causal inference methods now, and they are using different models, different strategies with different assumptions to identify the causal effect of interest. And among them, there is one method called instrumental variable analysis methods. So what is instrumental variable analysis? It's just a simple method, but that can help you to answer the causal questions using observational data only. And the main features of the instrumental variable analysis is that it does not require any model assumptions about the confounders. In other words, even you don't know or doesn't realize that the existence of the confounders, you can still use the instrumental variable analysis. So this is the main reason that why it becomes so popular in many fields. And particularly if you do many statistics work in the epidemiology and the genetics analysis, you will encounter the instrumental variable analysis very often. And the main advantage is not only that it does not require the existence of the measure of the confounders, it also gives you very flexible models. So in other words, you can have more choices than the model, not only modeling the phenotype distribution, but also the distribution of genetic association. This is a particularly important point I want to highlight today because we are doing many analysis in epidemiology and genetics. And usually, in many cases, you will find that the epidemiology analysis is more sensitive than the genetics analysis. So the reason is because that epidemiology analysis is based on distribution of the phenotype, but the genetics analysis sometimes are based on the distribution of the genetic association, which is more reliable and stable. So instrumental variable can be based on the distribution of genetic association. That is very popular in genetics. So right, what is the MR? So technically speaking, MR is nothing but just the instrumental variable analysis. So if you are interested in the MR, you can start to learn the MR, and also you can start to learn the instrumental variable, because every concept and every problems and every points in instrumental variable analysis is also the points in Mendelian randomization. But the key difference is that Mendelian randomization uses the genetic variance as the instrument, which is quite different to another other instrumental variable methods. So we will immediately realize that why MR is so different, because it uses the properties of genetic variance, and it will make.
Sorry, I have a question.
Yes.
What do you mean by the four analysis? MR is a four. What does that analysis method mean? It says MR is a four analysis method. Oh, Ivy, sorry.
Yeah, this is in short, stands for the instrumental variable analysis. All right, so technically speaking, MR is just an instrumental variable analysis method, and we'll start to first introduce the instrumental variable analysis, and then move to the why genetic variance can be used as the instrument. So when we talk about the causal inference methods, including instrumental variable analysis, assumptions are very important concept, because in causal inference, no assumptions, no causal inference. That's why we really highlight the importance of the assumptions. And so for instrumental variable analysis, there are three important assumptions. And this is perhaps my personal step. Before I introduce the assumptions, I prefer to introduce the purpose of the assumptions, because based on different assumptions, you can achieve different purpose. So today, our purpose is just only one. That is, we just want to test a null hypothesis. This null hypothesis is called the sharp null hypothesis, which means that there's no any causal effect in any way over any time. So this is a very strong statement. But you will quickly understand why I can only test this null hypothesis, because I only made three assumptions. So how do we introduce the assumptions? In causal inference, there are many different languages to describe assumptions. Usually there are three languages, and I list all of them. So in the very beginning, let's assume that there's no, I didn't make assumption. I just want to emphasize that we can write down the outcomes expressed by the expression and other variables. So this is the first equation I want to start. At this stage, I didn't make any assumption. I just write down the equation. This equation refers to structure equation, which represents the belief of how the data are generated. So here, the capital U refers to the any variables that it will be related to the outcome, but we just cannot observe that, we cannot realize that. And the parameter beta refers to the causal value we really want to test, because under the null hypothesis, we really want to test if not the beta equals to 0. So we write down the equations. And now, interestingly, if we assume there exists an additional variable, so this variable is actually like the genetic variant. And this variable, once we have this variable, we can update it, the graph and the equation like in this way. Again, at this stage, I didn't make any assumption, because I can always write equation like this way using the algebra language. So now we will start to make assumptions. So the capital G is the instrument, and the first assumption is that I assume that the G, that is the instrument, is correlated with the exposure. And then if I additionally assume that the instrument is independent of the confounders. And the third assumption is that I assume that the instrument cannot affect outcome directly. once we made these three assumptions, we say that the instrument G here is the valid instrument. So this is typically the three assumptions for the instrument variable analysis. Once we have this valid instrument, we can immediately write down a very famous equation in instrument variable analysis. That is to say, the genetic association with outcome is just proportional to the genetic association with the exposure in the size of beta. So the beta is the parameter we want to test. So the left-hand side is genetic association with exposure. The right-hand side is genetic association with the outcome. So we can use the statistical methods to make inference because they are identifiable in statistics. So we can immediately know what the beta looks like. So remember that we are testing the Sharp-Nine hypothesis. So we wish to find the evidence to distinguish the betas from zero. So once we find such evidence, we can say that there exists a causal effect, which means that the beta not equals zero. So this is a typical idea. So as you may know that we here made a very strong statement. So when we reject the Sharp-Nine hypothesis, which means that we can say that there exists causal effect, but we have no idea what this effect looks like. We don't know if or not the so-called causal effect is only applicable to certain subgroup or certain exposure level. And this is a trade-off. This is because we only made three assumptions because I don't want my today's presentation too complicated. So in causal inference, if you make less assumptions, you will only be able to test a very strong non-hypothesis. So this is a trade-off. If we want to answer more precise causal effect, for example, the causal effect for a certain subgroup, we must make more assumptions. But once we made more assumptions, sometimes these assumptions are unverifiable. So which means that they may be unreliable, they may be violated in realistic. So we will end up with unreliable results. So this is a trade-off. And so this is the first point I want to highlight today is that today we are only care about the Sharp-Nine hypothesis. We do not want to do the other things beyond the Sharp-Nine hypothesis because we only made three assumptions. And in most, I think in all causal inference methods, assumptions are very important. If you want to test the weak hypothesis or you want to do estimation, you must assume additional assumptions. So there is a very famous paper published in nearly 20 years ago in econometric. So that paper made additional assumption, which is quite reliable. And using that additional assumption, they can identify a very interesting causal effect, which is defined to a subgroup of the population. So that's if you are interested, you can look at this paper, and that paper is actually illustrates this idea in a very good way. And this idea is also the key contribution behind the 2021 Nobel Prize in Economics. So overall, this is about my today's work. We wish to use the IV3 assumptions to test the Sharp-Nine hypothesis. So here, I just give some examples of instrumental variable analysis. So the key ideas of instrumental variable analysis is just to find the valid instrument that satisfied all the three IV assumptions. And typically, all these scenarios, you can see that the instrumental variable is kind of good, which means that we believe that they are indeed somehow well randomized. So randomization is a very beautiful word in causal inference because like the RCT, it gives us the chance to do the causal inference. And in recent years, there are someone proposing to use the genetic information as the instrumental variable to do the causal inference. So because they think the genetic information are well randomized. So in other words, they believe there exists some randomization in a Mendelian way. So they call it Mendelian randomization. So we're back to Mendelian randomization. We already know the instrumental variable analysis and with the three assumptions to test the Sharp-Nine hypothesis. And then now we have the genetic information. So we are really interested to know if not we can use the genetic variance to do the causal inference under the instrumental variable framework. So can we do that? Actually, I don't know. Nobody can tell you the answer. But this is our belief that many people think genetic variants are kind of good randomized. So I want to highlight that this sentence is the belief, not the conclusion. And indeed, there are many people disagree with the Mendelian randomization. But today, I want to illustrate this point. It really depends on if or not you really believe the genetic variants are indeed randomized. Because if genetic variants are indeed randomized, we indeed can use the instrumental variable analysis logic to do the causal inference. So I think there are many good logic behind the MR. So the key philosophy is that if we look at the family level, so the Mendelian laws, I think, ensures that the distribution of the next generation's genetic factors are indeed kind of independent, so which means that they are well randomized. But most times the MR was conducted in the population level. So in the population level, there are many ways to think about Mendelian randomization assumptions. And I think random matching is the one logic to help you to evaluate if not the genetic variants are indeed randomized or not. But again, I want to highlight that this is just one way to illustrate it because nobody can really illustrate if or not the genetic variants are indeed randomized. And strictly speaking, also the random matching is not always correct in practice. But again, I just say that usually we're happy to believe that genetic variants are randomized in the sense that is typically independent of the environmental factors because the environmental factors will serve as the confounders in our instrumental variable analysis framework. This is the first point. The second point is that we already used the GWAS to identify the many genetic variants that are associated with the exposure of interest. So which is good because remember that the first IV assumption indicated that the instrument should be correlated with the exposure. And this is the truth because we already used GWAS to find that there's indeed many genetic variants associated with the exposures. So which is good. And also from the statistical perspective, since we have found many independent SNPs, we can do lots of statistical works like the meta-analysis to borrow information. That is to say, for example, we have 10 genetic variants. For each one of them, we can do the MR estimation and get the so-called causal effect estimates. And we can easily combine them together to have the more narrow confidence intervals or more confident causal conclusions. This is a very flexible idea in terms of the meta-analysis for instrumental variable analysis estimation. And also, since we have the multiple instrumental variables, we can also have the chance to do many robust MR methods, and we will return to this point later. So which is good, because if you really look at the other instrumental variable analysis examples, they only have one instrument, but in genetics, in MR scenarios, we can have multiple instrumental variables. So we can have much space to take advantage of such multiple instruments available to us. So this is about the second point. And the third point is also very important. This is also the truth, not the belief, is that genetic variants are usually fixed at birth, which means that if we happy to believe that genetic variants as the instrument. So the instrument is very fixed at the very beginning. It was not influenced by the later age phenotypes. So it will give you a quite stable belief about that your instrument is very good, it's very fixed. So if you are happy with the first point here and plus the third point here, I think you should be very excited about the Mendelian randomization as the instrumental variable analysis because it gives a very good belief to believe that the instrumental variable assumptions are well satisfied. So this is about all the logical point, and also I want to highlight some important things from statistics. So I really show that the very important equation of instrumental variable is like this. So the genetic association with the outcome is proportional to the genetic association with the exposure. So if we look into this equation, you can see that we actually no need to calculate it, the genetic associations with the phenotypes by using the individual level data, because GWAS have really done this for us. And also you can see that these two genetic associations are separated in the equation, which means that we even don't need to do the estimation using the one sample. We actually can finish the estimation using the two different data. So which means that we can using the two sample analysis. So this gives the MR quite flexible than other instrumental variable analysis methods. So here, this example is that so-called the two sample summary data Mendelian randomization methods, which I think is the majority MR methods for the published work in the recent years. And I want to highlight one point here is that the two sample summary data MR is very popular is because the convenience of data, but not because this method itself is more reliable. Because this is just because it's more convenient that everyone can use the published summary data and quickly to do the MR estimation. So that's why you can see if you look at the many published MR papers, typically they are about two sample summary data MR. Right, and another in the end point I'm going to highlight is that because we are the community of genetics, when we do the MR, we can do lots of things beyond the traditional instrumental variable analysis. This is because that we use genetic variance as the instrument. So if we look at the genetic variance, we can do a lot of things using the different genetic techniques. And for example, we have very good data sources from GWAS and TWAS. And if you wish to take the U exposure as the protein or expression level, you can also use many EQTL and PQTL. And also we can do lots of another works like FIWAS, like variance clustering, LD score, genetic correlations. So all these methods can help you to improve the reliability of your MR analysis. So that is to say, if you do MR, you can of course do lots of instrumental variable analysis methods, and also you can do lots of another genetics techniques analysis. Right, this is all about all the things and the motivations for the MR. But do we really think the MR is good instrumental variable analysis methods? And my answer is perhaps yes or no. Remember that if we treat the MR as the instrumental variable analysis methods, and everything is about three assumptions of instrumental variable analysis, but even we already know that there are many good properties of genetic variance, we still face many challenges in terms of the violation of the IV analysis method. So the first point is that the genetic association with the exposure is actually not quite strong as you expected. So which means that even we found that there is some evidence from the statistics that the genetic instrument is correlated with your exposure. It doesn't mean that your first IV assumption is really satisfied. So this is not a logical problem. This is about statistical problem. So because you estimated genetic association with the exposure is the estimate, so you must take into account the uncertainties for you in violation of IV strengths. So there is very famous and well-established metric to measure the IV strengths that is called F statistic. So that is to say, once you have decided your instrument and exposure, you can quickly calculate the F statistic. If the F statistics is less than 10, which means that you will suffer from the weak instrument bias. So what's the consequence of the weak instrument IV issues? Is that if you are using the one sample MR, you typically have the inflated type 1 error. This is very helpful because remember that what's the purpose of MR and the IV analysis? The purpose is just to do testing. So you will, when you get a meaningful conclusion, you typically want to reject your null hypothesis. But if you cannot control your type 1 error, your conclusion that rejects null hypothesis will not be reliable. That's why we really care about the F statistic value because it determines if not we suffer from the weak IV issues, particularly if we are doing the one sample MR. if the F status value is lower than 10, this is very dangerous, which means that any conclusion you get will be unreliable. So that's why we need to check F statistics in IV analysis, including Mendelian randomization analysis. So this is about the first assumption. And about the second and the third IV assumption, unfortunately, I would say that is typically not quite satisfied in realistic. So here I just pick the 8 examples to illustrate that the genetic variance can still violate the IV assumptions in many different scenarios, which means that even the truth is that there's no causal effect of X on Y, you can still find that your genetic variance to be correlated with your outcome. So that is to say you could end up with the false positive conclusion. So here, so this is very dangerous, but we cannot solve all the scenarios. And so the only things we can do is that we try different strategies to evaluate these assumptions, and we try our best to improve the quality of the MR analysis. So here I just give my suggestions to improve the MR analysis, because we cannot assume that genetic variants are very perfect instrument, in the sense that typically in many scenarios, the IV assumption will be violated for the instrument variable we used for the causal inference. So I randomly pick some suggestions here. So I think maybe we should be very clear about the exposure definition. So this suggestion doesn't actually change the MR calculation, but instead is a good habit, at least to me, it's a very good habit to be first very clear about exposure definition. Because in many scenarios, the MR exposure is not the true exposure, but actually the biomarker of the exposure. That is to say, many times we do the MR analysis based on the biomarkers or the downstream variables of the latent exposure. So in this case, you can still do the MR analysis, but you should be really care about the interpretation. So that is why we get the conclusion using MR. I suggest to use the sentence like, the genetically predicted exposure is associated with outcome, instead of to say there exists causal effect of the exposure on the outcome, because sometimes the exposure is not the true exposure you can imagine. So the exposure sometimes are only the biomarker of the latent exposure of interest. So this is an example about why I encourage you to be very clear about exposure definition. And there are also some suggestions. So for example, if you exposure of interest is the LDL. So for the LDL, we know that there are many biological confirmed pathway for the generation of the LDL. So you can use the specific prior knowledge to choose the genetic variants. That is, you don't need to use statistical way to choose genetic variants. You can just pick the gene regions that are most associated with the LDL-C. So this will increase the reliability of your genetic variant, because in the sense, you will truly believe that genetic variants are associated with the exposure of interest, and there is a low risk of the violating the third and second IV assumptions. And also you can do another check. So for example, most scenarios we do MR based on the published dual summary data. So one suggestion could be that think about how the summary data were generated. Because there are some scenarios that the GWAS was used in different way than you expect. For example, they use the BMI adjusted exposure. In this case, we know that from the GWAS, if we adjust the BMI, so some data could be not quite reliable. So it will make you some genetic variants to be will be unreliable and invalid, in the sense that it will violate some IV assumptions. So that is also the good habit. And we also have some suggestions to do the robust MR methods. So robust MR methods will typically or options that everyone can use in practice, because everyone typically can use robust MR methods. So my next slides will be introduce some robust MR methods. But before I move to the next slide, I want to emphasize one thing, is that robust MR methods is just one way to improve the quality of our MR analysis. So because I don't want to give you the impression that robust MR is the major things, and sometimes robust MR methods cannot help you. But it's just because that we can do the robust MR nearly in all scenarios. That's why I have to introduce them. But you can see there are many other strategies you can consider, but not only limited to robust MR methods. Right. So what is the robust MR methods? Robust MR methods refers to all the methods that can help you get reliable causal conclusion, even some or all IV assumptions are violated. Because we know that in the MR, the IV assumption can be easily violated. So that's why we need, sometimes we need the robust MR methods. So the robust MR method is based on the assumption exchangeability, which means that they propose the new additional assumption to exchange the original IV assumption. So even your original IV assumption is violated, but you use the robust MR methods, you can still get valid conclusion. That's the key idea. So either use different strategies. Usually, I think they can be divided to two groups. One group is based on the SNPs removal strategies. Another group is based on the model-based group. So I give you quick examples. So the MR model is the very simple method, which means that when you made the additional assumption that you believe the majority of the genetic variants that generate the consistent or similar IV estimates, they are the valid instruments. So this is the assumption. Under this assumption, you can immediately identify the true cause effect according to the cluster of the genetic variants. Another method is called the MR-APSS. So this is the completely statistical based and model-based methods. So instead, they directly use the algebra language to describe the distribution of the genetic association with the exposure and the outcome. And then here, they use the different assumptions based on the statistical model, and then make inference to get the true causal parameters. So this is a very model-based methods. Here, I introduce these methods. It's not because this is the good method, but actually it takes advantage of the LD score. So LD score is a method to describe the genetic correlation of your exposure and outcome. So it also, LD score is also based on assumptions. So MR-APSS is just use very similar assumptions behind the LD score to conduct robust IV analysis estimation. So we have so many robust MR methods. So can we choose the best methods out of these candidates? And my answer is no. Never do the selections on the robust MR methods. So the idea is that, as I said, the robust MR methods is to propose the new additional assumption to exchange the original IV assumption. Different methods will use different ways to propose the additional assumption. You never know which additional assumptions are more reliable in your scenarios, because most times the causal inference assumptions are unverifiable, which means that nobody can tell you they are really true. So in practice, the general way is used more like the triangulation strategies. That is to say, you should try multiple different robust MR methods, and you can say, if or not, they are really consistent. So if we use many different robust MR methods based on different additional assumptions, if we found that your conclusion is quite consistent, which is good because they will increase the reliability of your MR compilation. But sometimes we may end up with quite different results using different robust MR methods, but it's okay. In this case, don't be frustrated, just report your results. And this will motivate the future studies to think about why in some scenarios that your MR results are quite different using certain robust MR methods, and it will improve our understanding on your real application scenario. So this is the key ideas I want to say that. Right, so this is about robust MR. And here I just give the pipeline. So actually I'm a really anti-pipeline person because I have very mixed feelings about the proposed pipeline for the convolutional analysis. The reason is that on the one hand, the pipeline auto procedure is good because it can help us to get rid of some big mistakes. But on the other hand, it will give you the false impression that your MR analysis is good because when we do the MR analysis, when we finish all the checklist and we do all the correct things, we will tend to believe that our MR conclusion is reliable, but actually not. The MR conclusion is really based on the designs, but not from the calculations. So even you do all the calculations, that means that your MR results are reliable in the end. But generally speaking, when we do MR analysis, everything is just based on the question and your data. So you can have data and then have question. You can also have first have the question and data. Usually, I would suggest to first have the question because the question will make you think about, if not, you are doing the right design. You are really answer the question instead of just do the calculation based on the data. So there are many ways to start the MR analysis. So if you are doing the epidemiology analysis, it's very okay to directly say that, okay, we are interested to the causal effect of your exposure and your outcome. This is a very good motivation. And if you are to genetic variants, for example, you would think about the mining multiple protein candidate. You are interested to know of which or how many proteins are correlated or have the causal connection to exposure. You can also package it as the Mendelian randomization question. That is so that you can focus on each single protein and think about and do the MR for each single protein because single protein can be served as the exposure and your outcome will be served as the outcome in the instrumental variable analysis framework. And also sometimes you may have two phenotypes and you cannot distinguish the causal direction of the phenotypes. So you can also do the MR. So in the way that you do the first MR using the first phenotype as exposure and then do the second MR using the second phenotype as exposure. So I just do two MR separately. So this is the other thing, it's very flexible. You can very flexible to the MR analysis in any way you wish, as long as you can describe the question as the investigate the causal effect of X on Y. So the most important things later is about the SNP selection. SNP selection is typically the most important part in MR analysis. There are many strategies I proposed here. Again, once you have selected SNPs, you can do the MR calculation, which is very simple and straightforward. Any packages can do it very quickly. And then I think more important thing is to do sensitivity analysis. So you can do a lot of sensitivity analysis. For example, using different robust MR methods and based on different data cohort and using different genetic variants, because in MR you typically have many genetic variants can be used for the IV estimation. And then you can also do positive control and negative control. So these things will help you make your MR results is more informative and in the end more reliable. So that is about the conventional summary data MR pipeline. So let's give a quick summary. So we already know that MR is essentially just the instrumental variable analysis methods. So technically speaking, everything in IV analysis is also applicable to the MR. But the key feature is that MR using genetic variants as the instrument. So this good thing or sometimes a bad thing, because sometimes we are very happy or excited because of the property of the genetic variants, but sometimes we're also very frustrated because we know that genetic variants can violate many IV assumptions in many scenarios. So we still wish to do the causal inference using the MR. But MR here, I think is more kind of explorative methods. It's not the very final causal inference methods. I understand that everyone is very excited about the causal inference conclusion, but MR can only give you very initial assessment. So usually the typical application of MR is to first highlight the variables you think have the causal relationship. And then later you do another causal inference methods focusing on those highlighted exposures. So this is typically pipeline. Again, the very important features of my today's presentation is that we only introduced 3 IV assumptions. Remember that in causal inference, assumption is very important. How many assumptions were determined how precise conclusion you can get? Because we only use 3 IV assumptions. You typically actually doing the Sharp-Nunn hypothesis test. So this is very important conclusion that in most scenarios, the purpose of MR is just to do testing. We do not do estimation. We just want to test the null hypothesis. There's no causal effect. So the main conclusion of the MR is typically that we believe there exists some causal effect, but we have no idea what the causal effect really look like. So usually we will use another methods to solve this problem or use the advanced MR methods. And again, the really important feature is that the difficulty and novelty of MR are not from the computation. I want to say again is that the MR is very easy methods on my eyes, and it also uses very tiny data, particularly if you combine MR with other post-GWAS methods. MR is very simple, but I spend much time to emphasize the design because design is actually much, much more important than the calculations in MR. If you have very good design, maybe I understand this is very difficult because this is case by case, but if you can find a scenario that everyone are really happy, nearly everyone are happy with the IV assumptions, that they are really happy about you using that genetic variant to do the MR or IV analysis, your MR conclusion will be much, much valuable. That's very important because causal conclusion is very exciting, but there are so many causal conclusions published by MR papers in low quality. That's very frustrating. So we really happy with the good design MR, even your final conclusion is not significant. Because I understand because sometimes we have the pressures to publish in some papers, we really have to end up with significant results. But in causal inference, there is the so-called population bias. So that's why in causal inference, we're really happy to see causal inference methods like MR analysis with good design. Even your final conclusion is not significant. That is still very good papers. So that is typically all the summary of the MR for the for the traditional and conventional MR analysis. But of course, there are also some actually many advanced MR topics because I cannot look into each of them. But there are many advanced topics. I think they can be, again, divided to 2 groups. So the first group is more from the methodology perspective, or say the statistical perspective. So we can consider more complicated models. We can answer more precise causal effect. Because remember that if you only do the traditional MR, we are only to do testing. So the null hypothesis means that you believe that there is no causal effect, which this statement is too strong. Sometimes we are interested in a more precise causal effect. So that's why we need more advanced MR topics for the nonlinear and time varying and individual level causal effect. But again, this will require additional assumptions. When we do causal inference, when we make additional assumptions, we should be very careful about this because many assumptions could be violated in your application. So this is a trade-off. And another direction of the advanced MR is based on the application considerations. Because MR is the genetic epidemiology methods, sometimes we used MR in epidemiology and genetic scenarios. We need to think about some specific problems. For example, we need to think about selection bias. We need to think about the sample bias. We also need to deal with missing data. So how can we use the MR in such scenarios? There are many methods proposed so that if this problem is applicable to your application, you can consider these advanced topics. I highlighted some very good papers for each one of them. And also if you do the genetics data, usually we do multi-omics data and we have the protein or expression level And which means that if we do MR with them, we typically use cis-EQTL or PQTL, and it will also involve many statistical problems. And based on this, there are many novel methods proposed to help you to do the better MR analysis with cis-EQTL and PQTL. This is about the genetic side. And of course, we can also use MR with few hours. So this is quite flexible. So MR essentially is just a simple method, but this is actually the kind of conclusion that if you find some causal inference method simple, which means that this is better. So the simple method sometimes is better than complicated and fancy methods, but the design becomes more important. So you want to ensure that you do a lot of MR analysis, and you want to convince others believe that your MR conclusions are reliable. So you need to think about many scenarios in your specific application. So not only just doing MR in a mechanical way, you need to think about it like a more flexible ways to deal with all the potential problems you think there could be in your analysis. And right, I gave you a quick introduction to the one topic of the advanced methods. So MVMR is just a more generalized version of MR. So this is good because once you understand the this is good. I mean, if you understand the general version, you can of course understand the more special version. So the MVMR is good. So MR is good. The main reason I think is it can be indeed used in many scenarios. So in your application, sometimes if you using the causal mediation analysis, you can use the MVMR. If you are interested in some key risk factor selection problems, you can also transform it to MVMR. So here, MVMR is very flexible method. So that's why I highly recommend it to you. But again, this is about advanced MR topics. So if your application really consider various scenario questions, you can use the MVMR. Right, so this is about the MR part, and I want to extend a little bit to connecting MR to other topics.
Haodong, we have like 1 minute.
Okay, yeah, I just randomly picked one topic.
Thank you.
For example, if you think PRS, so PRS is typically, you can use the PRS with the individual level data, and it will have the individual level MR. Individual MR analysis is quite good because you can combine with many advanced IV and machine learning methods, because IV and machine learning methods are, many cases are based on individual level data. So do not limit your MR to the summary data level. You can do a lot of fancy things using the individual level data. So particularly if you have PRS, if you have individual level data, and you will get many interesting conclusions. So of course, we can connect MR to any other topics like genetic correlation, pharmacokinetic colocalizations. Right, this is about all the things. Here I also provide some MR learning resources, and I would thank all my friends for this slide. Thank you so much. Yeah. So any other questions, then be free to ask.
Thank you so much. And if you wanted to ask yours in person, you're here.
Well, I put in the chat earlier a question that what does it mean to say that the genetics is randomized? Like, obviously, I can get behind that being the case between the parents, but across everybody else, that's obviously false. So
yeah, this is a good question and also hard to answer, because if we look at the population level, the randomized actually means that the genetic factor of individuals, the individual's genetic factors are kind of independent of the environmental factors. So the environmental factors, because we are typically the confounders, and in IV analysis framework, we wish to say that the instrument is independent of the confounders. That's why we wish to say that the instrumental variables is independent of the confounders. So in other words, it's kind of randomized, because when we say something is randomized, we would typically believe that that thing is independent of other variables. So
yeah, it just seems to not obviously hold true for humans, right? Just straightforwardly be false.
Yeah,
I mean, yeah, for all of the reasons that we're familiar with in genetics, like genetic variation is not random compared to.
that's a good point because,
Yeah.
as I said, this is the belief. And there are some people disagree with Mendelian randomization because they don't believe that the genetic variants are indeed randomized. So this kind of debate, but if you are happy with the random mating, the random mating will give you the one motivation to believe that the genetic factors are randomized, but that's not guaranteed.
Thanks so much. And also just thanks for a beautiful talk. I love all your emphasis on all of the assumptions. And I was wondering, for somebody who was new to this field and you had a, well-formulated research question, and it sort of seems like you were saying that sometimes people don't have well-formulated research questions when they come in, but let's say they did, how would they go about really doing that work of working out what is the right method, what are the right sorts of assumptions? Are there like resources to get up to mastery of that?
Yeah, thanks for the question. So I think the main development of MR is actually all about assumptions. If you look at the slide, so assumptions is the most important concept in causal inference. Why we propose new methods is because that we believe some assumptions are violated. That's why we propose new methods. But new methods comes with new assumptions. So to some extent, you can say that everything is about assumptions. Sometimes we don't believe the assumptions are satisfied. That's why we do lots of sensitivity analysis. We want to tell the audience that, okay, I do lots of sensitivity analysis and triangulation strategies based on different assumptions. My results are still stable. So in other words, they want to show that, okay, I don't know which assumptions are correct, but I do many analysis using different assumptions. My results are still stable, which means that I think they satisfied all the assumptions, or they satisfy one of the assumptions, and our conclusion is reliable. So that is the key idea. Yeah, hopefully this answers the question. Yeah.
Great. And I think for time, we'll end there. Let's thank our speaker one more time.